Fermi questions. Fermi questions follow directly after the tennis ball discussion, and the tennis ball discussion is a great way to introduce Fermi questions because of the things, the topics, the ways you have to approach those questions to make sure that the mathematics you're doing, the explanation, the logic you're using, all that stuff makes sense. So Fermi questions, we first need to make logical assumptions. We also need to verify and make sure that we're talking about unit conversions in this. We don't want someone to get information in feet and then somehow give us information in meters without doing any of those conversions. And then upper and lower bounds, we need to make sure we know how to explain our way to see how we know that a number is too much and we know that a number is not enough, giving us an upper and lower bound. And then maybe coming up with a way to isolate some answer between those upper and lower bounds that gives us something logical, something that makes sense based on all the research and the information and the assumptions that we made. Now, making assumptions helps to make the mathematics easier, as long as you have logical assumptions that aren't too far-fetched, are in a relatively strict line of thinking. The logical assumptions help makes the mathematics easier. It takes irregular objects and maybe you assume that they're regular. So in a classroom, let's say with the tennis balls, you assume that classroom is rectangular or a rectangular prism. And now we all kind of know that in construction there's always imperfections. The angles aren't necessarily 90 degrees in the corner of the walls. Or there might be some decorative construction things like extra pieces of wall that stick out just for visual effect. So saying that it's a perfect rectangular cube helps make the mathematics easier, and it's just kind of a logical assumption that prevents us from having to do a lot more work, like measure the angles, measure distances, do composite figures, and figure out multiple different steps. Logical assumptions, again, makes the mathematics easier. The way that Fermi questions are approached when given this question is, how can you make some logical assumptions about this question? It doesn't necessarily ask you for an answer, but it gets you going in making those logical assumptions and maybe ways to figure out what you could do with an upper bound and a lower bound. So can every person in the world fit inside a cubic mile? What some of the assumptions we're looking at is that we can calculate the average size person. We're going to assume that we can figure out the amount of space the average size person takes up, and what this does is this eliminates the potential of having somebody that's very, very large and somebody that's very, very small and trying to calculate a whole bunch of different size people. Other things is that we know that the population is continuously growing and decaying, and so with birth and death, so we have to figure out maybe that there is some kind of constant population. And so what that does is that eliminates that minute by minute or hour by hour growth or decline in the population based on life and death or birth and death. We also maybe need to figure out, if we're talking about a three-dimensional cubic mile, like we're trying to put things into a box, or are we trying to put things along a two-dimensional space? Are we trying to represent this cubic mile in 2 dimensions, or are we actually representing it as 3 dimensions? And so we have to figure out the two-dimensional versus the three-dimensional calculations. And so if we're talking 2 dimensions, now we're talking about everybody standing inside of a cubic mile and only taking up basically that foot space. If we're talking about 3-dimensional cubic mile, then we're talking about now people are laying on top of each other, standing beside each other, and not only the 2-dimensional space is being taken up, but also that third dimension of height is also taken up. So this average size person now doesn't only talk about average space taken up in terms of their width, but also their average height. So you take into that third dimension. These are assumptions that you would have to make. I'm assuming we're talking about a cubic mile spread across some area of land in a 2-dimensional space. Or I'm assuming I'm taking this 3-dimensional object and I'm trying to put people in it like putting tennis balls into a classroom. So these are all different types of assumptions that you might have to make. Other things is trying to figure out an upper bound and a lower bound. Whenever you figure out those upper bounds and lower bounds, it talks about space between people. For an upper bound, the space between people would be none. For an upper bound, you would have none. No space between anybody. For a lower bound, you might have, let's call it a maximum amount of space between people. There's several different things that you can take into account for the assumptions and the mathematics behind it. But guys, that explanation piece at the bottom is the thing that we're trying to look for. Did they adequately, logically reason through this problem to make sure that everything was accounted for and that they were able to get a decent estimation within either an upper bound or lower bound, or a decent estimation that mathematically, that logically, based on their reasoning, makes sense? And did their reasoning make sense as well?